Let's finish up our discussion of arithmetic and geometric series, and we're going to discuss infinite series. Now remember what the word infinite means. It goes on forever and ever and ever. So if you're talking about an arithmetic series, that means you're going to continue to add or subtract some quantity forever and ever and ever. And the word series in this case means sum. So we're talking about adding up infinite amount of terms and to achieve a sum. And you stop and think about that for just a minute. If you continue to add or subtract, can we find a sum? And remember that in order to find a sum, you basically got to add everything up. So there has to be a limit in how many terms you have. And so we're kind of removing those limits now with an infinite series. So here's the idea. Take a look at this expression here. We have basically 0.1111. Okay, and so the question is, does that equal something, or does it have a sum? So let's ask the first question. Does an infinite series have a sum? Okay, well, let's take a look at our first example here. We have 3, 6, 9, and 12. And as you can see, this is an arithmetic series. So we know it's arithmetic now. All right, and so the question is, does it have a sum? Well, let's extend this. We know this dot, dot, dot here means it goes on forever and ever. 3 dots means it will continue on forever. So let's extend this now. We know that we're increasing by 3, so my next number would be 15, and plus 18, and plus 21. And this would continue to go on. So you can see that every single term is going to increase by 3. How in the world would I be able to add up all of these numbers if they continue to increase by 3 forever? So we're going to make a little hypothesis that an arithmetic series, because of that fact, has no sum, which means we'll never find a value that we can stop adding to it. And so therefore, there's nothing that we can do to find a total or a sum. So an arithmetic series, we're going to say in general, has no sum. Number 2. In example number 2, we see the geometric series 2, 6, 18, and 54. Now again, it's geometric because by inspection I can see that I'm multiplying each term by 3. So my R value, as you can see, 6 divided by 2 is 3. Well, that means that I'm going to continue to multiply every single term in this series by 3. Well, 54 times 3 is 162. So this is getting bigger and bigger and bigger. And what we're going to eventually learn is that if our R value is greater than 1, then a geometric series has no sum. Whoops, there we go. No sum. Let's take a look at this last example here. Here we have the geometric series 8, 4, 2, 1. Now, very, very quickly by inspection, you can see that the terms are basically halving in value. Okay, half of 8 is 4, half of 4 is 2, half of 2 is 1. And so if I continued on with this, I would get half of 1 is 1/2, half of a half is a fourth, and so forth and so on. So as you can see by inspection, these values are actually decreasing very rapidly, or my denominator is growing faster than my numerator is. So we will say that this does in fact have a sum. My R value is 1/2. This is a geometric series. And so we will say that this does have a sum. We'll say yes. Now here's the reason why. If your R, or your common ratio, is between -1 and +1, then your geometric series has a sum. However, if your common ratio is greater than 1, then your geometric series does not have a sum. The idea is very simple here. We're talking about two types of series. A convergent series basically means it moves towards, in this case, some value or sum. It happens because your common ratio is a proper fraction. It's between the values -1 and 1, and it has a sum formula of the sum of infinite terms is equal to the first term in that series divided by 1 minus the common ratio. So we can actually calculate the sum if our series is converging. Now again, what does that mean by converging? Well, in the last example, number 3, we had the series 8, 4, 2, 1, 1/2, 1/4. So as you can see, each value is decreasing or shrinking. And in essence, if we started to add all these up, we're going to add smaller and smaller and smaller and smaller quantities as if we were approaching something. This other type of series is called a divergent series. It means we're moving away. My R value, or my common ratio, is greater than 1, and we have no sum here. An example of that would be like example number 2 from just a few moments ago. Notice that every single time, every term, I end up multiplying by 3, and my values are getting larger and larger and larger. So as you can see, I'm not moving towards something, I'm moving away from something. Here's a good example to think about it. If you were standing in a classroom and you were, let's say, 50 feet away from the exit door, every step that you take, you start off with 2 feet, and then your next step's going to be 6 feet, and your next step's going to be 18 feet, and then your next step's going to be 54. I think it's very easy for you to imagine that you'd be able to walk through that door and leave the classroom. However, if you were 50 feet away and your first step was 8 feet, I know that's a big step, and then 4 feet, and then 2 feet, and then 1 feet, you start to notice, or 1 foot, you start to notice that you're taking smaller and smaller and smaller steps, and so you would approach the classroom door, but you would never be able to walk out of it. You would always be, in essence, 1/2 away, no matter how small this value got. And that's the difference between converging and diverging. So an infinite series can have a sum if it's a geometric series. In the geometric series, the common ratio, R, is between -1 and 1. The sum has a formula of the sum of infinite terms is equal to the first term divided by 1 minus R. So let's see if we can do a couple of problems here. We're asked to find the sum if possible. For problem number 4, which by inspection is an arithmetic series, it has a common difference of 6. As you can see, 6 plus 6 is 12, 12 plus 6 is 18, 18 plus 6 is 24. Since this is an arithmetic series, it has no sum. You would just write this as your answer, no sum. In problem number 5, we notice that we have a geometric series. My R value would be 3 divided by 9, which is 1/3. 1/3 of 9 is 3. 1/3 of 3 is 1. 1/3 of 1, of course, is just 1/3. We have a common ratio of 1/3. Now this common ratio fits our criteria up here, that is between -1 and 1. It's a proper fraction. So therefore, we should have a sum here. So the sum of infinite terms is equal to the first term divided by 1 minus R. My first term is 9. My ratio is 1/3, so my denominator becomes 1 minus 1/3. Now if you need to do this math off to the side, you can. This could become 3/3, that's 1, minus 1/3, which is equal to 2/3. So this becomes 9 divided by 2/3. Once again, this simply means 9 divided by 2/3, or 9 times 3/2. which becomes 27 over 2. So the sum of this geometric series will be 27 divided by 2. Let's take a look at one more example. Here we also have a geometric series. Its common ratio is 2. However, if the common ratio is not between -1 and 1, which means it's greater than 1, even though it's a geometric series, there is no sum. So let's go back to our first problem. Is there some value or sum that the decimal point 1111111 going on forever would equal? Well, I can rewrite this using fractions. So this one would be 1/10. This one would be 1/100th. This one would be 1 over 1,000, and so forth and so on. Now I need to determine if this in fact is a geometric series, and if it is, what is its common ratio? So I'm going to take the second term, which is 1 over 100, divided by the first term, which is 1 over 10. Rewriting this, I end up with 1 over 100 times 10 over 1. Keep the first term. Keep the first term. Take the and multiply by the reciprocal of 1/10. I end up with 10 over 100, which is 1/10. Since my common ratio is 1/10, I can now determine that this is in fact a geometric series, and it has a common ratio of 1/10, which is between -1 and +1. So if that's the case, what is the sum? The sum of infinite terms would be the first term divided by 1 minus r. The first term is 1/10. My r is also 1/10. I need to do a little bit of fraction math here. 1 minus 1/10, changing the number 1 to 10 over 10, end up with 9/10. So I end up with 1/10 divided by 9/10. Some of you know that you can just reduce out the 10. However, if you're not comfortable with that, we can rewrite this into a division problem. Keep the first term the same, change the multiplication, and take the reciprocal, and I end up with 1/9. Now, if you had some time after watching this video, you can take 1 and 9 and put it into your calculator, and it would give you the decimal point 1111. So remember, an infinite series has a sum if it's a geometric series, its common ratio is between -1 and 1 or a proper fraction, and its formula for infinite terms is the first term divided by 1 minus the common ratio. I hope this helps you in your studies with infinite series.